Section 5.6 sounds interesting. Inequalities in one triangle. But inequalities just allow us to get to the real goal of understanding how triangles can actually physically be made. Trigonometry really delves deeper into this, but this is a primer for a lot of those discussions. We already have established during our discussions of the triangle angle sum theorem that all the interior angles of a triangle must add up to 180 degrees. But that theorem assumes that the triangle has already been built. Once successfully built, the interior angles do add up to 180 degrees. This section deals with how you can actually successfully build a triangle. Let's say we have a triangle with two sides of length 8 and 9. There are many ways that you can build a triangle like that. This is one possibility. Here we have triangle ABC. At this point, many of you are thinking, whoop-de-freaking-do. We have a triangle. Yay? In this triangle, I have the two sides of length 8 and 9 like I said. The third side is just a tiny bit smaller than 1.8, but 1.8 will have to do as an approximation. I have also highlighted one of the angles in the triangle, angle B. I want you to think for a second about what will happen to this triangle if I want to keep two sides at length 8 and 9, but I change the size of angle B. Do you think you have a good idea of what will happen? I'll run an animation here and focus on what happens to our triangle as I change the size of angle B. Angle B keeps getting bigger and bigger. So we started with a small-sized angle B and worked our way up. Hopefully you saw that the size of the two sides never changed. There was always one side of length 8 and one side of length 9. However, the side opposite from angle B changed when angle B changed. As angle B got bigger, the side opposite from it got bigger. If you didn't see that happening, go back and rewatch the animation and focus on what happens with angle B and its opposite side, line segment AC. Plus, it took me a while to create the animation, so the more love it gets, the better. The point of the whole animation is that in a triangle, the smaller the angle, the smaller the side opposite from it. And the larger the angle, the larger the side opposite from it. It just has to be like that when you try to form a triangle. Angles and opposite sides are inextricably linked. You need to get that basic idea down. This brings us to two very generic theorems. There isn't even a name for them, that quantify this idea. The first one fits exactly what I just did. If two sides of a triangle are not congruent, then the larger angle lies opposite the larger side. This is a generic theorem. It won't be used in a proof or anything. You just need to get the idea down that larger angles have larger opposite sides. The second theorem tackles it from another direction. If two angles of a triangle are not congruent, then the longer side is opposite the larger angle. So it works that way too. Larger angles have opposite larger sides. Larger sides have opposite larger angles. Both work. These theorems both specifically mention that the sides or angles are not congruent. You should already know what happens if they are congruent. If they are congruent, then you have the isosceles triangle theorem, and the converse of the isosceles triangle theorem. It's the same kind of idea. Math classes obviously present you with a new idea, then often show you problems illustrating that idea. In the case of this concept, when you make problems showing this idea, you end up with things like this. This is a typical question you might see. The idea being that to find the smallest side, you have to find the smallest angle, and the side opposite from that smallest angle will be the smallest side. The medium side will be opposite from the medium-sized angle, and the largest side will be opposite from the largest angle. Simple, right? But you can also solve this problem by just looking at it. It's common sense. Or if it's close, you could use a ruler to determine the right answer. So that's kind of a cheap way to get to the answer. In these types of problems, it's common for you to see it like this. The problem will say that the picture is intentionally not drawn to scale or something similar. Just to warn you not to trust your ruler or whatever to come up with the answer. You must use the concepts. And it shouldn't take you long to realize in this picture that this angle is nowhere close to measuring 157 degrees. You must use your concepts. For this one, you would first need to fill in the missing angle. Then you would look to find the smallest of the three angles. I really hope that's not hard. The side opposite from the smallest angle is the smallest side. Then you find the medium angle. And the medium-sized angle is opposite from the medium-length side. And finally, the largest angle is opposite the longest side. This isn't terribly difficult. You just need to be aware that these problems often have pictures where they are not drawn to scale. Now let's consider what it actually takes to build a triangle. Would sides of length 12, 16, and 40 successfully make a triangle? Some of you may already know, but if you tried to build one, it would end up like this. The sides of length 12 and 16 just can't get together. They can wave at each other, they can pine to be together, they can stretch all they want, but they can never connect with one another. The problem is that dang side with length 40. It's just too darn big. But you can probably imagine that if the large size side kept shrinking, that it would eventually be short enough that the two shorter sides could have their long-awaited kiss and finally hold hands. The trick is finding out mathematically exactly when we can make a triangle and when we can't. That brings us to the triangle inequality theorem. The sum of the lengths of any two sides of a triangle is greater than the length of the third side. This is the theorem that can check whether you can form a triangle or not. There are 3 checks to make in order to determine whether you can form a triangle or not. I originally had this question: could I form a triangle with sides of length 12, 16, and 40? So we make 3 checks. First, 40 plus 12 is bigger than 16, so that works. 16 plus 40 is greater than 12, so that works. But the last one fails. 12 plus 16 is not bigger than 40. Even though there are 2 true inequalities here, the one false one is enough to say that no, you can't make a triangle out of it. But 3 checks seems like a lot. The theorem does say you should check them all, but in practice you only need to check the 2 smaller values compared to the biggest value. If there is no biggest value, then it won't matter which you do, it will definitely work out. This is the last one that I drew that worked out. The 2 sides finally got to kiss. There are 3 checks to make according to the theorem, but the only one that might fail is the one where you check the 2 small values compared to the biggest value. But the only one that might fail is the one where you check the 2 small values compared to the biggest value. So this is the only one that you really need to check. If this one works, then they all will. Just check the 2 smallest versus the biggest. If you want, you can check the other 2, but they will always work out if the biggest value is on the left side. That seems like a waste of time, but if you want to do it, you can. I won't stop you. One last point with this. Sometimes you will get a question like this. First, the numbers are out of order. Oh my, whatever will we do? You still only need to make that one check, the sum of the 2 smallest compared to the biggest. But when you make this check, they come out equal. The theorem and the question clearly say greater than, not greater than or equal to, so this does not work. Equal does not count. It must be bigger. You will often have problems like this. Now we no longer want to know if 3 given lengths can make a triangle. We want to know all of the possible values that the third side could be. The book tells you to just apply the triangle inequality theorem, which is fine. You end up doing this. Setting x to be the length of the unknown side, you apply the triangle inequality theorem to get these 3 inequalities. Then simply solve for x. Then the book tells you to think it through, or plot it out on a number line. But if x is greater than 3, and x is greater than negative 3, then you can just collapse those two into simply x is greater than 3. And then you also know that x is less than 13, and that's your final answer. That's perfectly fine. You can do it that way you want, but there's another way to do the same thing that is much easier. You are given lengths of 5 and 8. The first answer is if you just subtract them. You always subtract the smaller number from the larger number. We don't want negative distances, but other than that, all you're doing is subtracting. The other answer is if you just add them. There's no problem with adding. Add in either direction that you want. Those are your 2 boundary conditions. The only real trick is figuring out if it is x is greater than 3 and x is less than 13, or if it is x is less than 3 and x is greater than 13. It's going to be one of those 2. Students can normally figure out pretty easily which one makes sense. Only one will. So that's your answer. It's just an alternate way to do that type of problem. You are simply adding and subtracting. That's it. Pretty easy. I hope you can add and subtract. Just to bring this full circle, think back to the first animation that I did, where I changed the size of angle B, and the opposite side started small and got quite big. The length of line segment AC changed a lot. Based on this last concept, you now should be able to calculate all possible values for the length of line segment AC. 2 of the lengths never changed. AB was always 9, BC was always 8, and you just simply add and subtract. 9 minus 8 equals 1, and 9 plus 8 equals 17. So the range of possible values for my animation was AC was greater than 1 and AC was less than 17. Remember, it is greater than and less than. It is never greater than or equal to or less than or equal to.